So one of the things that we talked about is given a theory, one can have some parameters such as masses in the theory, Newton's constant, all these wonderful numbers that show up within a theory. And these can just be sort of nailed down parameters. You sort of say the fine structure constant is 1 over 137. And, your explanation for this is it just is, and this is a fairly natural number. However, in a more broad class of theories, these are things that people like Bekenstein have looked at, you take these constants and you promote them to fields. Right. And instead of this number, instead of G being a constant, for example, and you looking at Einstein relativity, you look at Brans-Dicke theory, where G is a field and it varies from point to point, and it's covariant and all very, very nice. You have to be careful about how you do this, of course, because just putting G of t in doesn't work. You have to make this a nice covariant field, but nonetheless, there are ways of doing this. As such, if you say that these parameters are now fields, does that alleviate any claims of fine-tuning? Because the fact that we see, alpha to be 1 over 137 roughly, might just be a dynamical result of its initial conditions.
Right. So in that case, we don't have, they're not free parameters anymore. They're the sorts of things we'd like to go and calculate. This is kind of the something we thought was a fundamental parameter turned out to be just an environmental variable. And we've seen this before in the history of physics. So Kepler tried to explain the distance of the planets from the sun via this sort of wonderful nested series of the Platonic solids. So I've forgotten the order, but you put the sphere of Mercury's orbit, and then you put like a cube, and then another sphere, and then a tetrahedron, and it almost works. It's great. It doesn't quite work, and then you have more planets than just the 5 Platonic solids. So that's a shame. It turns out that the distance from the Earth to the Sun is more like an environmental variable. There's other planets elsewhere in the universe. It can be different. So if something we thought was a constant turned out to be actually something like a field, then in testing that idea, we go for the fundamental parameters of that theory. So it has been suggested actually that these ideas have been floated, and you can test them in observations of distant galaxies, distant quasars especially. So the fine structure constant is about electromagnetism, so it affects how electrons orbit around atoms, which affects the light that they give off when they jump between the orbits. So if you go looking at distant quasars and the light that comes from them, then you might be able to spot that, way back in the early universe, this parameter was different. One of the reasons to be suspicious of that idea a priori, before you actually do that, is you think about, okay, suppose it is a field. Then it has the field properties. So for example, it has, a quantum field is basically the stuff that particles are made out of. You make a field wobble in a certain way and it looks like a particle. This thing would do exactly the same thing. So there would be a particle, it would need to have a certain mass, and to have the value of the field, the strength of the field, which is really the value of the constant now, moves so slowly over the size of the universe that we can only just see minor variations if we look at a quasar billions of light years away. Suddenly, okay, what properties would the field need in order to explain that? And it needs to have suspiciously fine-tuned properties. So you would need you could talk about the mass of the particle that the field has if you make it wobble, is a way of talking about the properties of the field. It would need to have an extremely small mass in order to be so constant over the size of the universe. And then you're back to another fine-tuning problem. So you can push fine-tuning problems around without ever solving them. But the way you might solve them is by saying, okay, rather than, if the properties of the universe change so much from place to place that somewhere it must have got the right combination of values, then maybe you have a solution to the problem of fine-tuning, because even even I guess it says that there's no real fundamental parameters at all. They're all just environmental variables being mixed up, and you just get the right properties at some point.
So this sort of brings you into what John Peacock calls the ensemble approach, and sort of goes under the heading of multiverses if you take this to its sort of natural limits. And the idea is that sort of in these cases you have these low probability events. So, for example, things being fine-tuned. And the way that you explain them is you artificially somehow, or at least within your theory, you come up with a way of generating a large number. So that the probability of any one thing happening, the probability, for example, of me winning the lottery, is very, very small. But of course, someone wins the lottery. And therefore, if you look around the country, there are a large number of people, so you can probably find a lottery winner. And so if you look at these models where you let the field vary from point to point, perhaps on some axis perpendicular to our own space-time, of course this is how you get into these multiverses that people talk about, but nonetheless you could come up with a nice model where, for example, Newton's constant slowly varies over scales much larger than our Hubble horizon. You could create these sort of separate places where eventually within one of them you would find the right conditions for our existence. But in doing so, you're naturally invoking some kind of notion of anthropics. Right? I mean, we have no way of sort of deciding what those set of requirements on our existence really are. So, for example, would you be happy, if you could explain everything with these sort of set of ensembles, but there's no reason why, you had 2 arms instead of 3?
Right. Depends how ambitious you are, I suppose. So if you want to, so the important thing about that kind of explanation, the multiverse explanation, you need sort of 2 ingredients. You need the variation, and you need enough variation that given that these quantities, whether they're constants or variables, need to be in a certain narrow range to get life. You'll need a lot of variation in order to hit the bullseye. If the bullseye is small enough and your aim is terrible, then you need to throw a lot of darts. You need that. You also need some sort of selection effect that that tells you why you observe the one that hit the bullseye. In this case, it's because we are, life, and so, if observers only turn up in universes that are fine-tuned, then you have an explanation there in 2 parts. There is a universe with observers in it at all, because there are lots of universes, and one of them was going to hit the bullseye eventually. And we observe ourselves to be in that kind of universe because we are observers. So it's that second one, which is called the Anthropic Principle. Has a bit of a checkered history. It's been defined in a whole heap of different, some more useful, some less useful ways. But I think of it simply as a selection effect. So these are very familiar if you're an astronomer. So whenever you do a survey of the universe, if you point your telescope at a blank part of the sky, you will observe only the things that are bright enough to observe, which seems like a fairly obvious thing, but actually in practice you have to be careful, because you want to make a statement about the population of, say, galaxies out there, but you don't have the population. What you have is a sample, and the way you got your sample is not necessarily by just sort of picking at random. You got the brightest things. You got the things that were bright enough to be seen. And so, for example, you might notice that the further away, if you've got a way of measuring the number of stars per galaxy, you might notice that the further away the galaxy is, on average, it has a higher number of stars. Now, that doesn't mean that in the population of galaxies out there in the universe, that the further away from Earth you get, the more stars there are in your galaxy. All it means is that at further distances, the only things you could see were the big bright things. The other galaxies might be there, but you couldn't see them. So it's a statement about your sample. It's not necessarily a statement about the population. So in the multiverse, we have that situation of that we are observers. And as you say, there are some tricky sort of cases there about exactly how much you could hope to explain. But again, theory testing is theory comparison. If there's no other theory that can do better than a multiverse plus Anthropic Principle, then there's reason to think that that's the way the universe actually is. So if there are some clear-cut cases, and actually fine-tuning for life is what we sort of hope gives these cases. If, for example, there's a fairly rapid transition in, say, the cosmological constant, so there's a form of energy which is making our universe expand exponentially quickly. So, we're coming into a phase now in the universe where things are getting further apart, but if you wait for it to get twice as far apart, it'll then, after a billion years, wait another billion years, it'll be 4 times, another billion years, it'll be 16 times further away. So things are just blasting their way out. Under those circumstances, the formation of structure will simply stop. So the things form in the universe when gravity binds things together. You have an over-density, you have a lump of matter here. This is the short story of galaxy formation. That the rich get richer. A lump of matter will attract more matter and get bigger. But if once your universe starts expanding exponentially, there's nothing else close enough to be drawn in. If you have a nice cutoff there, that there's a point where, as the cosmological constant goes up, the point at which the universe starts expanding exponentially becomes earlier and earlier in the universe. And this was Weinberg's argument in 1987. Past a certain point, that will happen before any structure has formed. In which case, you don't have to worry about the details of life and all of that. You have a universe which is really simple. It's very easy to calculate what happens. Nothing happens. It's just uniform, and it stays uniform. All the complexities of what I do, galaxy formation, all the simulations, all of that sort of stuff, they're difficult because gravity is making things collapse, and there's all sorts of things going on. In these universes, if you just turn the cosmological constant up enough, nothing happens, right? Everything just expands too far away for gravity to make anything collapse on anything else. You have a wonderfully simple universe and no one around to appreciate it. If that transition happens really quickly, that happens fairly quickly, then you have what looks like the beginnings of an explanation of, okay, why is the cosmological constant in this range? Given that it has a huge sort of possible range, the Planck scale is an awfully long way away in 120 orders of magnitude. But we have an explanation of why we're here. Maybe it varies in other parts of the universe. And if you're not in this range, then you can just forget about it. There's no one observing these universes out here. You have the start of what could be an interesting argument there. I mean, Weinberg predicted that the cosmological constant would be non-zero, have a certain value, and he did that sort of 10 years before we discovered that it did have a non-zero value. So the argument has pedigree. It also has a lot of assumptions.
So in these cases, in the Weinberg argument, for example, one uses the Anthropic Principle, the fact of our existence, to put bounds on the Copernican principle, the principle of mediocrity, that we should find ourselves, in a typical position within the universe.
Yes.
So if you sort of take this, this argument very seriously, what you would then say is that sort of the combined principle is, in some sense, that we should find ourselves to be a typical observer in the space of observers that could exist within the space of your theory then.
Yeah, I think that's a useful shorthand way of thinking about it. It's a slightly, when you do it in practice, it's a slightly frequentist way of thinking about it. So what you would do in that circumstances is you have a population. There will be within that population there will be regions that have a certain value of the constant. And to say that we're typical is to say that if most observers observe this sort of range, that we're, here's the peak. If we're sort of somewhere near the peak, then we've sort of explained why we have that value. That's testing a theory using only its ability to predict the data, but it's not a bad rule of thumb. Certainly if that were false, if most observers in your favored multiverse theory would observe a cosmological constant that turns out to be 1 billion times smaller than what we observe, then we're in a bit of trouble. That seems like a wrong prediction. Again, in the sort of Bayesian framework, that would be an opportunity for another multiverse theory to come along and do better.
There's also a real sort of fundamental issue here as well, and how you define an observer, right? Because for every you or me or every cosmologist there's billions and billions of ants, for example. So if you took a sort of principle of mediocrity across all observers and said it's equally probable that you're a human or an ant, given that there are so many more ants than humans, why would you believe in this principle if you find you're not an ant?
Right. So this is an interesting point. So there's one of the reasons why frequentism is not one of the superiorities of Bayesianism over frequentism. Frequentism has this problem called the reference class problem. So if I want to say, what's the probability that this particular lottery was rigged? If frequentists would want to know is how many times has this kind of lottery been done, and then how many times has this type of lottery been done and rigged? And you take the ratio of those two. Now, the problem with that is, what do you count as a lottery? Does it have to be the same company doing it, the same balls, the same person pulling the balls out? Or do you go wider? Do you say any old bingo hall will do, the local club that does a bingo night, that'll do? So there seems to be an arbitrariness in how you define those reference classes. You're supposed to be saying how many of this kind of thing divided by how many of that kind of thing. And there doesn't seem, in a lot of cases, there's no in principle way of saying what kind of thing should I be interested in. So that comes back to this problem. We're supposed to be saying how many observers observe what I see versus the total number of observers out there, and then you're in a reference class kind of problem. In principle, what I think the Bayesian would want to do is to define things what you could do is push way up one end of the scale and say, all right, let's just take all the arbitrariness out, and what we're interested in is when we're calculating just the likelihood, not the probability of the theory overall, but how many of the people who have exactly my set of observations see what I see. So you can, in a sense, Bayesian wouldn't put it this way. You push that reference class in nice and close, and you do things that way because you're calculating sort of hypothetical things anyway. So you don't need to be counting actual examples. So this is quite a difficult problem. I'm not sure if Bayes has all the answers to this. It's very much an area of debate in the literature. In particular, how time comes into this. If you have two identical civilizations, but one of them lives twice as long as the other one, should I count that one with twice the weight of the first one because it's made twice the number of observations, or should I just be counting observers? In which case, it seems like you might penalize civilizations with long-lived members. That's a very odd sort of conversation. All of that smacked to me of a reference class problem. If you're getting yourself into this sort of tangle, you're asking the wrong type of question. One of the other reasons why Bayesianism is so attractive to scientists, it seems to be leading us to the right questions and leading us away from these sorts of, what kind of thing am I really interested in, sorts of questions. But I don't think there's any generally agreed solution to this within it's still an open debate in the literature. One I'd very like to know what the answer is.
Yeah, I mean, I think it's a really sort of fascinating and open problem, and I think one of the really sort of interesting topics you hit on there is the idea of the time ordering to these things, or whether there's some sort of natural precedence in the order of facts somehow. For example, as a Bayesian, I might say, okay, it may be I start with a prior of it being equally likely I'm a human being and a cat, and then I make a few observations like I see hands, and not many cats have hands, so I update my information a bit, and then I would then start to make deductions and then say the likelihood that I'm a human sort of tends to peak rather close to 1 as I make more and more observations of my environment.
Right. I think there's a problem with seeing... So there's a narrative about Bayesianism, which is that it's about updating. That you're sort of born with a set of priors. If you want to find out what the prior probability of general relativity is, you go to the kindergarten and you ask all the people there. And then Bayesianism is about updating. You start with a prior, and what you mean is you start in time with a prior, and then life is just a sequence of, I get new information, I update my prior, that becomes my new prior, I update. That becomes my new set of things I believe about the world, and then I just keep updating that as I go. That sort of narrative, I think, is... You can use Bayes' theorem in that way. It's quite useful to say, let everything I knew before, yesterday be my prior information, and then I'll update it depending on what today. But there's no... In these sort of the Jaynes way, the Cox way of approaching things via, let's just try and put a number on plausibilities, one of the assumptions is that it shouldn't matter the order in which you learned things. That those are equivalent states of knowledge. If you think of a simple example of that. But in that case, this sort of insistence that a Bayes theorem must be applied in chronological order is kind of against the basics of the theory. So it leads to something that is discussed a lot more in the philosophical literature than in the statistical literature, called the problem of old evidence. So if you're doing this kind of updating, you learn, if you lived in 1900, you learned about the perihelion shift of Mercury before you learned about general relativity. So when you come to test general relativity, supposedly, what you say is, what's the probability of the perihelion shift? Well, I knew that already, and so general relativity hasn't changed that at all. I think that's the sort of problem you get into if you insist on doing things chronologically. You then would have to... You then have people saying, oh, you can only be a Bayesian if you are sort of born omniscient and you thought of every theory to start with. I think that's a complete muddle of what actually happens in what the real sort of Bayesian approach is, which is, who cares what order you learn things in? And then Bayes' theorem, this what's prior information, what do I update with, is purely convenience. It's not a matter of what you learned first and learned second. It's purely a matter of, okay, if I just had the probabilities, I wouldn't need to do this at all. I wouldn't need Bayes' theory. I just have the probabilities. I just need some help calculating things. And if the set of things I know can be split nicely into things I can calculate with and things I can calculate probabilities of, then I do it that way. Who cares what order I learnt them in? So this updating, I'm quite skeptical of. It's so common that it's a common way to talk about Bayes' theorem, but I think it could be misleading. So in particular, I don't think I need to do things like... The reason why this is relevant to fine-tuning, I should say, is people say, but the first thing I learn is that I'm alive. It's this problem of old evidence is, there's like the very first thing that I observe
right, you go back
tells
to
me that I'm an observer, right? So it's... I learned the perihelion shift and then I learned general relativity. Well, I learned that I'm an observer before I did any of this sort of stuff. And so it should be assumed in all of this. I think that's this order of things problem. What I should be doing is saying, okay, what can I calculate probabilities with? And what should I be calculating the probabilities of? And I can say, all right, let's suppose that I have a model of the way the world works, which is what theoretical physics is trying to do. And when I think about fine-tuning for life and multiverses, I now say, okay, I would like that to explain certain things about the world. Of course, you might have a model of galaxies or a model of the way water flows, all that sort of things. I can apply my scientific idea to myself, to life, to this universe, to its life-permitting properties. And if I do the things in that order, then that kind of makes sense of both scientific testing and of fine-tuning.
So when you talk about these parameters, I mean, I think it's very nice to sort of put this in terms of what I calculate with and what I calculate probabilities of. It seems that what you would like to do in a lot of these cases is move things from the with side to the of side. You want to sort of have fewer and fewer parameters, for example, into your theory, and calculate the probability of making these observations within it.
Right. Yeah, that's a good way to put it. So, in essence, that's the perihelion shift is such a good example. That really what you have to do with Vulkan and all of those things is that you're really sort of putting in the answer by hand. So it's sort of an extra assumption that you're calculating probabilities with. Whereas for Einstein, he can't put that in by hand. There's no extra spare dials to turn. It will either come out, it's something he's calculating the probability of, the prediction of what the perihelion shift will be. It either falls out of his equations or it doesn't. So when it does, happy days.
Well, I think to be fair here, I mean, you could introduce another planet in Einstein theory if you wanted to. You could have introduced another planet Vulkan. It's just you didn't need it. I think it comes more back to sort of the Occam position, which is that you didn't need to introduce anything new by hand, and that's why it's a... Yeah,
I suppose you'd put it that way. You could try the same sort of move in general relativity, but then there's no winner in that race. Right. So, for example, there's no winner in the race between Newtonian gravity and general relativity for Neptune. Right. They both have exactly the same predictions. It's only when you're close into the sun that you actually get a difference between the two.
But I mean, that's an interesting case as well to sort of turn on its head, right? Suppose we'd never seen Mercury. Suppose, our telescopes were only just about good enough to pick out Neptune.
Right.
And Einstein comes up to you and says, hey, look, I've got this theory of the universe. I think it's better than Newton's theory. And he says, look, it calculates all the things that Newton's theory does, and it agrees in all these regimes. I think it's nicer. How would you then distinguish between the two theories that made identical predictions in this case?
So that, I think, is one of the strengths of the Bayesian approach, that there's also this prior probability of the theory, that we do test is the wrong word, we do sort of rank theories, we do approach them according to things like mathematical elegance and number of assumptions, those sorts of things. So you will hear physicists, astrophysicists especially, saying of Mond, even if it explains the data, it's such an ugly theory. There's so many free knobs and dials, and it's such an ugly theory. But there are some sort of surprising ways in which a theory can be elegant. It can explain things that you didn't think you needed to explain in the first place. So my favorite example between these two, so in Newtonian gravity, there's the story of Galileo dropping a cannonball and a shot off the Leaning Tower of Pisa. Probably never happened, but it would have been great. And they hit the ground at roughly the same time. So this is not what you would expect in Aristotelian physics. And so in Newtonian theory, that supposedly explains this, but actually it needs a fairly strange assumption to explain this. So there's actually two ideas of mass here that are sort of blended together. There's, in Newtonian theory, if you think of F equals ma, if you remember that equation, the m in that equation is inertial mass, which is if I kick something, how hard is it to move? Which doesn't depend on gravity. If I was in outer space and I tried to push an elephant, I'd still have to give it a big push to get it going. Then there's the other type of mass, which we think of as kind of weight, which is how heavy is it how hard is the elephant to lift? Within Newtonian gravity, these are two totally separate ideas, but to explain the shot and the weight, to say why gravity, when it accelerates things, accelerates equal masses the same way, you have to say that these two numbers, inertial mass and gravitational mass, are exactly the same. So it's, in the right set of units, it's exactly as hard to push an elephant as it is to lift an elephant, is one way to say it. Now that is simply assumed in Newton, But you have to be thinking conceptually to see that. It passes so quickly in most undergraduate courses, you don't really see a problem. But then when Einstein comes along and says, actually what gravity is space-time itself curving and warping, and things don't really follow, in Newtonian gravity, things follow a curved path, and gravity sort of pushes things around in the curve, whereas in Einstein it curves space itself. And so the reason the ball and the shot follow the same path is that they both think that that's the straightest way through space-time. And so there's nothing about the strength of a pull, there's nothing about how hard they are to push, there's none of that. The equivalence of inertial mass and gravitational mass in that just falls out quite naturally. So in that case, that seems to be a very big reason for Einstein. You can think of it as a fine-tuning case. What's the ratio of gravitational mass to inertial mass in most objects? And to explain the data in Newtonian theory, you have to assume that those are the same for everything, for no deeper reason in the theory. Whereas here comes Einstein, that number will be exactly one for everything because it's space-time. That seems like a win, a massive win for the theory.
So to put it another way, what you might say is that when you recover Newtonian mechanics from Einstein's theory, there's a symmetry between inertial and gravitational mass.
Yeah, you could say that, yeah. Which
inherited from...
Yeah, you calculate of rather than calculate with.